Hey everyone, and welcome back to AI Paper Podcasts. Today we are diving deep into a paper that's been making some serious waves in the world of optimization.
It's called Iterate to Accelerate, a unified framework for iterative reasoning and feedback.
Catchy title, Ray.
Yeah, definitely grabs your attention.
And it's by Jacob Fine-Ashley,
Who actually went above and beyond and provided these really clear, plain English explanations for some of the key points in the paper.
Yeah, which is amazing. It makes it so much more accessible.
For sure.
Especially because this paper is tackling a pretty complex topic.
Yeah, it gets into the nitty-gritty of how to make algorithms converge faster and why feedback loops are so essential for certain types of problems.
Which is like music to the ears of anyone working in AI or ML, right? I mean, who doesn't want their models to train faster or their robots to figure things out quicker?
Absolutely. It's like the holy grail of AI research.
So before we get too deep into the weeds, let's give our viewers a quick rundown of the paper's key takeaways, just for that short form edit ready.
Okay, shoot.
All right, so what's the big takeaway here? What's the one thing that everyone should know about this paper?
Well, I'd say the main contribution is this unified framework for iterative reasoning.
Okay, break that down for us. What does that even mean?
It basically shows how a bunch of different optimization techniques can be viewed through the same lens.
Interesting. So it's like finding a common language for all these different approaches.
Exactly. And that common language is Bregman Divergences.
Bregman Divergences. Okay, now you're just using fancy words to sound smart.
Haha, fair enough. But trust me, they're not as scary as they sound. Think of them as a way of measuring distances, but in these funky non-Euclidean spaces.
Non-Euclidean spaces. All right, now I'm really lost.
Okay, so imagine you're trying to measure the distance between 2 points, but instead of a flat plane, you're on a curved surface, like the surface of a sphere.
I see. So the usual straight line distance doesn't really work anymore.
Exactly. You need a different kind of distance measure, and that's where Bregman divergences come in.
Okay, so why are these Bregman divergences so important for AI?
Because a lot of the data we deal with in AI doesn't live neatly on a flat plane. Think word embeddings or image features. They exist in these high-dimensional spaces that are all curvy and complex.
So those traditional Euclidean distances we learned about in high school, they just don't cut it anymore.
Right, they don't capture the true distance between points in these complex spaces.
So Bregman divergences give us a more accurate way to navigate those AI landscapes, so to speak.
Precisely. And that's why they're so crucial for understanding Fine-Ashley's framework.
Okay, I'm starting to get the picture.
Yeah.
So how does this framework actually work? How does it help us make algorithms converge faster?
Well, one of the key things it does is introduce a generalized iterative update scheme.
Generalized iterative update scheme. Sounds complicated.
It's actually not that bad. Think of it as a recipe for updating your algorithm's state with each step. You take into account things like the current state, a chosen update operator, and even potential errors or perturbations.
So it's like giving your algorithm a set of instructions for how to move through this funky non-Euclidean space, always getting closer to the optimal solution.
Exactly. And what's really cool is that Fine-Ashley proves that under ideal conditions, this scheme achieves a convergence rate of 0.1T2.
Hold on. Convergence rate 0.1T2. You're losing me again?
Okay, sorry. The convergence rate basically tells you how quickly your algorithm is approaching the best possible solution. And 0.1T2 means that as the algorithm iterates, the error decreases quadratically.
Meaning
it's getting more accurate really, really fast.
Got it. Faster convergence equals faster results, and everyone loves that.
For sure, it's like a speed boost for your AI.
So this all sounds pretty amazing, but there's got to be a catch, right? Nothing's ever this easy in AI.
Well, there are some conditions that need to be met for this optimal convergence rate to hold. Things like smoothness and contractivity of the function you're trying to optimize.
Smoothness and contractivity. Okay, so those are two more fancy words I need to add to my vocabulary.
Basically, smoothness means your function doesn't have any sudden jumps or changes. It behaves nicely. And contractivity means that applying the function repeatedly brings points closer together, like a shrinking map.
So if our function is both smooth and contractive, we're basically guaranteed to zoom in on the solution quickly.
Pretty much, yeah. That's the ideal scenario. But even when things aren't perfect, this framework still offers some pretty impressive advantages.
Now there's one more thing I wanted to touch on before we move on to the deeper dive. You mentioned earlier that feedback loops are essential for certain types of problems, specifically those involving fixed point functions.
Oh yeah, that's a key insight from the paper.
But I have to admit, that whole fixed point thing sounds a bit abstract to me. Can you give us a more concrete example of what you mean?
Sure. Think about finding the equilibrium point of a system. Imagine a pendulum swinging back and forth. Eventually, it settles down at its lowest point, right? That's a fixed point.
So in AI, these fixed point functions represent some kind of stable state or solution that we're trying to find.
Exactly. And Fane-Ashley's work shows that algorithms with feedback loops like recurrent neural networks or those using chain of thought prompting can approximate these fixed points much more efficiently than feed-forward models.
And by efficiently, we're talking about the difference between polynomial scaling and exponential scaling, right? That's a huge difference.
Exactly. It's like comparing a rocket ship to a bicycle.
All right, so we've got these powerful Bregman divergences helping us navigate complex AI spaces. We've got this iterative update scheme that converges super fast under the right conditions. And we've got feedback loops playing a crucial role in approximating fixed point functions. It's all starting to come together.
That's great to hear. But the real beauty of this framework is that it doesn't just live in the realm of abstract math. It has real-world implications for how we design and build AI systems.
And that's what we're going to explore in the next part of this deep dive. We'll talk about the practical applications of these ideas, the potential challenges, and the exciting future directions of this research. So stay tuned.
We'll be right back. So we've talked about how Fane-Ashley's framework relies heavily on Bregman divergences.
Yeah, so he's giving us this whole new way of thinking about optimization in these really complex AI spaces.
Exactly.
But I still feel like we could unpack that a bit more for our viewers. What exactly are Bregman divergences and why should they care?
Sure. Imagine for a second that you've got these 2 points in some super high-dimensional space, like 2 vectors that represent complex data.
Okay, got it.
Now a Bregman divergence, it's basically a way of measuring the distance between those points, but it's not like the simple straight line distance we see on a map.
Right, because we're not dealing with those neat little 2D planes anymore.
Exactly. We're in this wild non-Euclidean world now, where things can get all curvy and weird.
So these Bregman divergences, they take that curvature into account.
That's the idea. They give us a way to measure distances that make more sense when you're dealing with the geometry of these complex AI problems.
Okay, I'm starting to see the appeal here. But how do these Bregman divergences fit into Fane-Ashley's framework? Like, how are they actually used?
Well, they're a key part of analyzing the iterative update process. Remember that generalized update scheme we talked about earlier?
Yeah, where you're basically taking steps to get closer to the optimal solution.
Right. So Bregman divergences, they help us quantify how much progress we're making with each of those steps and how quickly we're converging to the best solution.
So it's like using them as a yardstick to measure how well our algorithm is performing.
Precisely.
Right.
And one of the coolest results from the paper is that under the right conditions, this iterative scheme can achieve that really impressive O1T2 convergence rate.
Right, the speed boost we were talking about earlier.
Exactly.
But let's talk about those conditions for a minute. Because Fane-Ashley, he uses some pretty technical terms like smoothness and contractivity. What do those actually mean in the context of AI algorithms?
Good question. Smoothness in simple terms means that your function doesn't have any sudden jumps or weird changes. It's like a smooth curve.
Okay, makes sense.
Contractivity.
Contractivity basically means that as you apply the function over and over again, it brings points closer together. It's like a shrinking map.
So if we have a function that's both smooth and contractive, we're in good shape, right? Our algorithm should converge pretty quickly.
Exactly. And that's one of the big advantages of Fane-Ashley's framework. It gives us a way to design algorithms that actually satisfy those conditions so we can take advantage of that accelerated convergence.
Nice. So we're not just hoping for the best anymore, we're actually building algorithms that are designed to converge quickly.
Right. It's a more principled approach.
Now, I remember you mentioned earlier that feedback loops are super important for approximating fixed point functions. Can we dig into that a bit more? I'm still not totally clear on why feedback loops are so crucial in this context.
Absolutely. Think about it this way. With a feed-forward model, like a typical neural network, you have data flowing in one direction, input to output. It's a one-way street.
Okay.
But a feedback loop, it lets information flow back from the output to the input. So it creates this cyclical process. So the algorithm is learning from its own outputs and refining its calculations as it goes.
Exactly. And that's super important when you're dealing with these fixed point functions.
Okay, but remind me again, what exactly is a fixed point?
A fixed point, it's basically a state where you can apply a function over and over again and nothing changes. It's like finding that perfect balance point.
Okay, I see. So how do feedback loops help us find those balance points?
Think about it like trying to solve an equation, but you don't know the answer right off the bat. So you start with a guess, and then you keep plugging it back into the equation, refining your guess each time based on what you get.
So it's like The feedback loop is guiding the algorithm towards that fixed point by constantly making adjustments.
Precisely. And one of the key things that Fain-Ashley proves is that for approximating these fixed point functions, feedback architectures are way more efficient than feed-forward ones.
And when we say efficient, we're talking about that difference in scaling again, right? Polynomial versus exponential.
Exactly. It's a night and day difference, especially when your problem starts to get really big.
So feedback loops, they're not just a nice to have. They're essential if you want to solve these types of problems efficiently.
That's a great way to put it.
All right. So we've got Bregman Divergences helping us navigate these complex AI spaces. We've got this iterative update scheme that can converge super fast. And we've got feedback loops playing this crucial role in finding those fixed points. I'm starting to see how all the pieces of this puzzle fit together.
That's great to hear. But the real beauty of all of this is that it's not just some abstract mathematical theory. It has some really concrete implications for how we build AI systems in the real world.
And that's what we're going to talk about in the final part of our deep dive. We'll explore those practical applications, the potential challenges, and what the future holds for this exciting area of research.
So stay tuned. We'll be right back.
Okay, so we've spent a good chunk of time talking about the theoretical foundations of Fain-Ashley's framework.
Yeah, we've really dug into the math behind it.
But now I want to shift gears a bit and talk about the practical side of things. What does all this mean for people who are actually building and deploying AI systems in the real world?
Well, one of the biggest areas where this framework has potential is in optimization. Finding the best possible solution to a problem.
Right, like when you're training a huge neural network or optimizing a complex control system.
Exactly.
Yeah.
Those are the kinds of tasks where traditional optimization methods can be really slow and inefficient.
Especially when you're dealing with tons of data and really complex models.
Yeah, it can be a real bottleneck.
So how does Fain-Ashley's framework help? Does it actually make things faster in practice?
That's the goal. The whole idea is to provide a more principled and efficient way to reach those optimal solutions.
And remember that O1T2 convergence rate we talked about.
Right. That translates to some serious speedups in training time and problem solving.
So it's not just some theoretical pipe dream. It actually has the potential to make a real difference in real-world applications.
Exactly. And it's not just about speed either. The framework also emphasizes robustness, being able to handle noisy data and all those imperfections we encounter in the real world.
Right, because things rarely go exactly according to plan in the wild.
Exactly. So we need algorithms that can adapt and still perform well, even when the data is a bit messy.
And that's where those perturbations come in, right? The ones that Fain-Ashley includes in his update scheme?
Yeah, those are there to model those real-world uncertainties.
That we're not just assuming everything's going to be perfect and clean.
Nope. We're building in some flexibility to handle the unexpected.
Now, all of this sounds incredibly promising, but I'm sure there are challenges too, right? I mean, translating these really abstract mathematical concepts into actual algorithms that we can use, it can't be a walk in the park.
Oh, definitely there are challenges. One of the big ones is scalability. These methods work really well on smaller, well-defined problems.
But when you start dealing with those massive data sets and super complex models that we see in modern AI,
things can get a lot trickier. It's like trying to fit a square peg into a round hole sometimes.
yeah, you've got this elegant framework, but the sheer size of the problem can make it tough to apply directly.
Exactly. So finding ways to scale these methods up is a huge area for future research.
And another challenge, I imagine, is finding that sweet spot between theoretical guarantees and practical performance. I mean, the paper lays out some pretty specific conditions for achieving that optimal convergence rate.
Right, but in the real world, those conditions might not always hold perfectly.
So we need to figure out how to make these methods work well, even when the assumptions are a bit fuzzy or when we don't have all the information we need.
Exactly. It's a bit of an art as well as a science.
Now, before we wrap up, I'm really curious to hear your thoughts on the future of this research. Where do you see this going in the next few years? What are you most excited about?
Well, one area that I'm super excited about is applying these ideas to even more complex and dynamic systems. For example, multi-agent scenarios, where you have lots of AI systems interacting and learning from each other in real time.
Or how about reinforcement learning,
Yeah.
where you've got an agent that's learning through trial and error in a really complex and changing environment?
Exactly. Those are areas where optimization is absolutely critical, and I think Fain-Ashley's framework could be a game changer.
So it's not just about making existing algorithms faster. It's about opening up whole new possibilities for AI.
Yeah, it's about pushing the boundaries of what we can do.
Well said. Well, I think that's a perfect note to end on. So To all our viewers out there, I highly recommend checking out Fane Ashley's paper, Iterate to Accelerate.
It's definitely worth a read.
It's thought-provoking, and it might just spark some new ideas for your own work.
And as always, keep iterating, keep learning, and keep pushing the boundaries of what AI can achieve.
Thanks for joining us for this deep dive into the fascinating world of optimization. We'll see you next time on AI Paper Podcasts.